okay over the topics on the last lecture. So there is a video lecture that is posted, and don't know why, maybe out of stupidity, that video came to be 2 hours long. Okay, all right, so today's lecture number? So it has to be number 8, right? If I posted 7, so today's lecture number 8. So effectively, what actually we will do on the first part, we will, in principle, summarize what we did in lecture 6 and 7, and then give you the complete solution to the system of equations AX equal B. So effectively, we will finish elimination today once and for all, trying to summarize the general solution to AX equal B. And I do hope that I have some time to talk about the basis for the fundamental spaces that we have seen up to now. Okay, so hopefully we will be able to do some progress in that domain. I'm going to doing some slide jumping today, so I'm going to slide 3. So I'm going to talk about the complete solution to AX equal B. All right, so let me go away so I can see what the slides are about. So we are, so what I'm going to do actually on the first slide, if you have noticed in the way Professor Strang organizes his book, he has a summary of every chapter in the beginning and at the end. So that way, if you can ever reach the end, you will know what the topic is in the beginning. So let me do the same thing just in case I cannot finish the lecture today. So we want to find a complete solution to AX equal B. So we have A, we have B, and we want to find the solution to the system of equations. And remember, we're not only interested in square matrices, for any matrices, okay? Now, you will appreciate that if you can find one solution to AX equal B, and we call that a particular solution, then you can add any solution from the null space, and you will still have a solution. So the idea is here, find a particular solution and add to the general solution to the null space problem, the AX equals 0, and then you have the general solution. And that's what you have to do in homework 1 on the last problem. So find one solution of AX equal B, any solution that gives you AX equal B, and add it to the general solution to the null space problem. So we will do this today as well. And we will actually emphasize once more today that this process of elimination, doing linear combinations of rows on the augmented matrix that involves A and B, and effectively going at the end to this reduced row echelon matrix Rx equal to D, contains all the information that we need not only to compute the solution to the null space problem, but also to compute the particular solution. So if you do the whole elimination, the answer is in front of you, and we will see it today. I am not going to do the derivation. The derivation was in lecture 6 at the end, and also I put the derivation on lecture 7. So, but we will see today how it works. Okay? Now remember, when you do elimination, right, some rows are going to come to be 0, completely 0. And why is that? Or what does that mean if one row during the elimination is completely 0? When will that happen? When will you get a row that's completely 0? And we put those at the bottom. When that row was some linear combination of earlier rows in the elimination process, okay? So effectively, it's like we don't need that row. If we don't need it, it appears during the elimination process to be all 0. Okay, now imagine that if you do this elimination process, right, and you get all zeros in this matrix R, the only way that you can have a solution, any solution, will be that the right-hand side of the vector B corresponding to this 0 row has to also be equal to what? Has to be 0. So if you get like the matrix R, 1 row, 0, and suddenly you have 25 for that vector D, there is no solution. So the system of equations is what we call it inconsistent. You cannot solve it. Okay? So we will see examples of that as well. So I mentioned to find the complete solution, we have to add a particular solution to the general solution of the null space problem. And how do you compute a particular solution once you have done the complete elimination all the way to this hard matrix? Effectively, you set all the free variables equal to 0, and then you solve for the pivot variables. And actually, as we will see, the elimination makes it so simple for you. You don't have to solve for anything because the pivot variables are multiplied literally with an identity metric, so the answer is already on the right-hand side. Okay? But theoretically, you put the free variables equal to 0, and whatever you get, let's say by back substitution theoretically, right? That's the particular solution. Okay. Now, if it happens, so for a matrix that is m by n, that the matrix is what we call full rank, and we will talk about this today. So if R is equal to n, means there are no free variables, and the solution to the null space is only the 0 vector. You remember the number of free variables is n minus r. So if we don't have that, then we call the matrix A as a full column rank, okay? And no free variables. And obviously, since I define a full column rank, I can also define a full row rank, R equal to M. In that case, the column space is the whole of Rm. Okay? The column space is the whole of Rm. And it says there Ax equal to B is always solvable. So it's always, we have a solution. Can somebody give me a reason why, if R equal to M, I always have a solution? From where is that coming? I mentioned this a few minutes ago. If R is equal to M, how many 0 rows do I have during the elimination process? None. So if I have none, I don't have to worry about having a non-zero element on the right-hand side, right? Because there is no right-hand side corresponding to that 0 row because there's no 0 row. So basically, the idea here is for any B, I will be able to find the solution. Okay? And again, this is a summary of the whole lecture today, so we're done. So I'll see you on Wednesday. I meant not physically, mentally. All right. You cannot even take a joke. All right, so let's see these things that we discussed today with examples so we can understand what they mean. So we have this 4x3 system of equations, okay? You can see immediately there are some issues here. For example, I can see column 3, right? Column 3 is what? Is the sum of columns 1 and 2, okay? And because column 1 and 2, they look different, right? So the rank of this matrix is how much, you think? If we do elimination, how much do you think the rank is going to come to be? So it cannot be 3. So what will it be? I mean, you can look at how many independent rows or columns you have. So how many independent columns or rows you have here? Rows is you have more than, you have 4 to decide. But if I look, let's say, at the first 2 columns, they look very different to me, all right? So R equal to 2. Okay. Now, I am not going to do all the algebra for this problem, right? But I just want to highlight the methodology, and we will come back with other examples. But can you check visually by plugging in this in here that this is the general solution to the null space problem? Remember, if the null space, if R is equal to 2, the dimensionality of the null space has to be equal to what? Haven't defined literally dimensionality, but how many free variables do you have in this problem if R equal to 2? The number of free variables is n minus R, so how many of those? 1, okay? So without doing the algebra, I just want to get a sense of what's going on. Can you check with me that 1, 1, minus 1 is a solution to the null space problem. If you put 1, 1, and minus 1, right, effectively you will get 0. Why? Because column 3 is the sum of columns 1 and 2. All right? So the general solution to the null space problem is what you see there. Okay? Now, just so we can make this problem interesting, can you verify for me that a particular solution to this problem is maybe 1, 0, 0? If you put there 1, 0, 0, can you solve this? Is that the solution to this system of equations? If you put 1, 0, 0? You remember the right-hand side looks to me like the first column. So 1, 0, 0 is a solution. And will you also agree with me that 0 minus 1, 1 is a solution? If I subtract from column 3, column 2 from column 3, what do I get? I'll get 2 minus 1, 1, 2, and 3, and 4, which is the right-hand side. So this is, these two vectors that you see there are particular solutions to this problem. Okay? So when you look at the solution of the system of equations Ax equal to b, okay, you first notice it is basically a line that passes through these points, and this line does not include the 0 point. So one of the things that sometimes we take it for granted, when you solve Ax equal b, the solutions of Ax equal b do not form a subspace. So when you solve Ax equal b, the solution does not pass through the 0 point. You remember the null space is a subspace, but the solutions of Ax equal to b are not a subspace. Okay? And the reason is you look at these 2 points. You can actually verify. I haven't done the algebra here. But you can verify that if you connect these 2 points on a straight line, any point in that line satisfies Ax equal to b. Okay? I mean, you can easily see this. So if you take, some coefficient times this vector plus 1 minus that coefficient times that vector, it's a solution to this system of equations, Ax equal b. Okay? That line does not pass through 0, so the solution of Ax equal to b is not a subspace. All right. So let me start talking about elimination so I can make some of these things more concrete so we can see how the algebra here works. So we have a system of 3 equations with 4 unknowns. This is my new system of equations. 4 variables. This is the right-hand side, and this is the augmented matrix. So what I'm going to do is I am going to start doing elimination. You don't have to read anything on the slide. It talks about the elimination process. So in the elimination, we will first get rid of what number? I do elimination here. What number should I get rid of start? 1. All right, so we will get rid of 1. And possibly then we will have to get rid of whatever we get where that 3 is. So let's see what's going on. So if you do all of the above, this is what you get. And again, may I advise you that you take half a minute to actually, when you go home or when you study this, to actually do the elimination process, right? And see indeed that the reduced row echelon matrix looks like that. Now, can you guess why the last row came to be all zeros? Well, it came to be all zeros. Why is that? Let me see. Why the last row got eliminated? Because, look at the last row. It's the sum of the first 2, right? So, and we are lucky that this system is solvable because 7 is equal 1 plus 6. If that 7 was an 8, I cannot solve this system of equations. All right? I can solve it because 7 is 1 plus 6, so that 7 also gave us a 0 during the elimination process. So this is the augmented row echelon matrix that looks like this. So how many pivot variables I have? What is R? R equal to 2. What variables are the pivot variables? X1 and X3. So the variables X2 and X4 are free variables. All right. And in this example, actually, we're lucky because there was a 0 there, all right? You can see there was a 0 from the start, so we really did not have to, you know, create that 0. That 0 was there to start with, okay, above the pivot element 1, so we did not have to worry about this in this example. Okay. So I just talked that basically in our case, the right-hand side was correct, so I don't need this, okay? Now, let me go back to, so don't pay attention to what says here on the right-hand side, okay? So actually, you know, so you don't really pay any attention to anything. Let me go back to this matrix there. Can you tell me now a particular solution looking at this matrix? So you told me that the pivot variables is x1 and x3. And you remember from the previous 2 lectures, the nice thing we identify with variables x1 and x3, that they're multiplied there. This matrix, the sub-matrix inside R, is the identity matrix. So how do we define the particular solutions or a specific particular solution of AX equal B? We take the free variables equal to what? To 0. So remember, this matrix R, the first part, right? The 160 is the right-hand side. This first part contains the identity matrix multiplying x1 and x3, and then what we call the F matrix, which is 3, 0, 2, 4, multiplying the free variables. And that is equal to the right-hand side, which is 1, 6, and 0. And we said that to find the particular solution, we will put the free variables equal to 0. So can you tell me what is then the particular solution if you put, so you have an identity matrix, then another F matrix equal to the vector 1 and 6. What is the particular solution when the free variables are 0? What is the particular solution? Remember this, there is here hidden a system of linear equations, right? There is the identity matrix, and next to it you have this matrix 3, 0, 2, 4. If you rearrange and you put the pivot variables first and then the free variables. And this whole thing is, when you multiply with the pivot variables and the free variables, you get 1, 6. And we said to get a particular solution, the free variables, we set them to 0. So looking at this system of equations, how much are the pivot variables? 1 and 6, thank you. Why is 1 and 6? Because we have the identity matrix, which is 1, 0, 0, 1, multiplied by the pivot variables equal to 1 and 6. The rest of the variables disappear. Why? Because we take them equal to 0. So effectively, you can read the particular solution to this problem by looking at this there. That's the particular solution, 1 and 6. Which means when you submit your homework, don't start using other weird methods you learned in high school or here and there. I want you to do the elimination process all the way and tell me what the solution is by looking at this matrix, right? Which means if you have done it differently, you have to start working again in your homework problems. You still have 2 days, okay? All right, so the particular solutions, let me just go to the next slide. So the particular solution is what you see here is 1, 6 for the pivot variables, x2 and x4, the free variables are 0, right? And you can verify, always verify, multiply this by 1060, and you see you do actually get 160. So obviously the x that we get after the elimination process is the same as solving AX equal B, because the solution is not be affected by row operations, so we don't have any issues with that. Okay, so let me so summarize based on this simple example. So I'm going to put everything up. This is exactly actually what you have to do in your homework, what you see on this slide. So you have to compute a particular solution, all right? And the particular solution in our case is 1, 6. It's this one here, 1060, okay? Remember, when you extract the particular solution, this is with the rearrangement of the variables where the pivot variables are first and the free variables are second, right? So when you write the solution X, the pivot variables are X1 and X3, X2 and X4 are the free variables that you put 0 and 0. Okay, now, for this particular example that you see here, okay, how many free variables we have? 2. So we need to compute how do we call this the solutions of AX equals 0? The null space, what do we call them? The free solutions or the spatial solutions? This is what, in Strang's book, he calls those the spatial solutions, okay, of the null space problem. So basically, the spatial solutions in the context of what I may discuss today, they are forming the basis of the null space. There are 2 independent elements in the null space. So this matrix R that you see here with the vector D immediately tells you what the spatial solutions of the null space problem are. You don't have to do any algebra. So based on what we did in the lecture last Friday, and lecture 7 that you haven't followed yet, okay? Can you remind me, how do we compute the spatial solutions of the null space problem? In simple terms, simple words, without looking at the equation. I mean, what are those? So I have 2 variables, X2 and X4, that they're free. So what do we do to define the spatial solutions? We take each of the free variables and we give it what number? Say it again. We give it 1, and the other one 0. And then, with those 2 free variables, 1 and 0, we solve for what other variables? We solve for the pivot variables. And you can do this, right? Exactly. Then you go and you say x2 equal to 0, x4 equal to 1, solve again for the pivot variables, and what you will get is, you will get actually those 2 vectors that you see here. You notice the second vector has x2 equal to 1 and has x4 equal to 0. And this vector has x4 equal to 1 and x2 equal to 0. And here now are the great news. You don't really need to plug in the values of x2 and x4 to this linear system of equations and solve for the pivot variables, because the answer is directly embedded in that R matrix. So where is that minus 3 coming from? Where is the minus 3 coming from? You take that 3, you make it minus 3, this is what goes here. Where is the minus 2 and minus 4 coming? This is the 4th free variable, right? You take that 2, you take that 4, you make it minus 2, minus 4, that's it. So those numbers are in the matrix F that we had defined in the previous lectures when we partitioned this matrix R. You remember the matrix R contains the identity matrix multiplying the pivot variables, and then this matrix 3, 0, 2, 4 that multiplies the free variables. So minus F is what is coming in here, all right? So minus 3, minus 0, and minus 2, minus 4 is what is coming on the spatial solutions. So effectively, if you do the elimination correctly, no further algebra is required. You just look and you say, there is the particular solution in 1 and 6. Just remember, you have to rearrange the labels of the variables, because 1 and 6 are the 2 pivot variables, which are x1 and x3. That's why you see them here in locations 1 and 3. And then you take the spatial solutions, you set x2 equal to 1, x4 0, x4 equal to 1, x2 equal to 0, and these other numbers, you extract them from the matrix F by reversing signs. And why you extract them from F and you reverse sign? Is that magic? No, the proof is in the notes, and you should read it. and it's in the video from lecture 7 and also in lecture 6. So there is a proof that that actually works. Okay? All right. So elimination basically tells us everything, and we don't have to do much algebra. All right. So let's consider this trivial example. Okay. So the matrix A here, it's 3 by 2. Okay. And obviously you can realize that the rank of this matrix, we have an issue here, right? Because you can see this third row is, if you sum the first 2 rows, minus 1 gives you basically row 3. So obviously the rank of this matrix at the very best will be equal to 2. And indeed, if you do elimination for any right-hand side, so if you first get rid of that 1, get rid of the minus 2, and this is what you get. All right, so elimination in general will give you this. And also you notice we put a 0 there because to define, so you don't forget, to define this row echelon matrix, you also have to put zeros above the pivots. It's very important. So, and in the pivot elements, what do you have what do you need to have? What numbers you have in the pivots? 1. All right, so 1 in the pivots, 0 above the pivots. So this system of equations, when you do for the general right-hand side, B1, B2, B3, right? It gives you something like that. So if somebody asks you, what conditions do you need for B to have a solution, what will be your answer? What should be the constraint between B1, B2, B3 to have an answer? Looking at this system of equations, what will you say? I'm asking the same thing I asked twice before today. Remember 0 row, and then suddenly on the right-hand side, I don't have a 0. So what conditions do I need to have a solution? B1 plus B2 plus B3 has to be equal to? Equal to 0. Yes? I mean, sometimes I'm wondering, right, when I say this, am I asking you the trivial things? And I always want to assume that I don't ask you everything trivial, okay? And I will know actually how trivial things are when I get back your homeworks and I look at them. But if I ask trivial things, please let me know. I mean, so I don't want to go too fast because I worry that we will not learn anything. But, if I bore you, please just say that, there's better things to do in life than listening to my linear algebra lectures. Okay, so B1 and B2 and B3 has to be equal to 0. Can you see, what is the rank of this matrix? Don't look, you told me that R equal to 2, all right? So what is the solution here to the null space problem? I have 2 columns and R equal to 2. All right, I have 2 columns and R equal to 2. So what's the solution? You remember how many free variables do we get? N minus R. How many are those? What is N minus R here? 0. So the only solution to the null space problem is 0. And based on what I told you before, can you extract directly the solution to to AX equal B? So the particular solution, can you tell me what it is? Yes. Whatever you have there, 2B1 minus B2, B2 minus B1, that's the solution, done. And you can verify, actually. You can go and put this up there, and you will see that it must satisfy the equation, say, X equal to B. Okay? So this case that you see here, right, so is what we call a full column rank, because the 2 columns of this matrix are independent, and the null space solution is basically 0. Okay. So let me, so I can start for you to help you to see the general case of this matrix R. So let's look the generalization of this full column rank case where m minus n is, where n minus r is equal to 0, right? So we're going to take the case, think of r equal to n, and look at this. Are you convinced that the general form of the reduced matrix R is the identity matrix, which is basically R by R, which is n by n, and then this matrix of zeros? Will you agree with me that's how R will look like? What happened? You remember there was an F matrix there. What happened to the F matrix? The F matrix was multiplying what variables? When you do in general, right, the elimination, you get an identity matrix, and then you get another matrix that we call it an F. The identity matrix multiplies the pivot variables, and then the F matrix multiplies which variables? The free. How many free variables we have here? None. So this is how this thing looks like. All right? It looks R equal I and 0. So this problem, all right, we said the null space is the 0 vector, but this problem, to have a solution, what constraint do we need to have? Because there is a 0 there, we need to have a 0 where? So this matrix, right, can be a long matrix, so m much bigger than n, okay? So an elongated matrix, that's why we get the zeros there. So the corresponding right-hand side on the vector B as we do elimination needs to have zeros. If it doesn't have zeros during the elimination process, then there is no solution. Now, if it has zeros, how many solutions this system of equations has? How many solutions can you get me? So let's say the right-hand side corresponding to that 0 is 0. So there are solutions. How many of those? How many free variables? How many free variables on this problem for full column rank? 0. So how many solutions to AEX equal B? If there are solutions? Say it. 1. Only 1. Right? So in this case, either we have no solution or we have one solution. Okay? So when we will not have any solution, if the right-hand side corresponding to that 0 matrix is basically something that is non-zero. But if it is 0, then there is only one solution because there are no free variables. Okay. Okay. So let me discuss another possibility now, which I'm going to call a full row rank. Can you imagine now what does full row rank? Before, the columns were independent. What does now full row rank means? And tell me how the matrix R is going to look like. What does full row rank means? That the rank R is equal to what number? For m by n? Equal to m, okay? So we don't have to worry now about zeros below the way we had before. So if we have a full row rank, we always have a solution, right? We don't have to, so there is a solution for any B. But we can have one solution or we can have many solutions, okay? So can you tell me how the matrix R looks like if I have a full row rank? So remember, the R matrix has the identity, then this matrix filter multiplies the free variables, and then it has another 0 matrix below and another 0 matrix. So for a full row rank, there are no 0 matrices. So how does the R matrix looks like? I'm going to have the identity, and then what else? Before, I had the identity, and I had zeros. So how, in this case, for a full row rank, the matrix is going to look? The identity, and then? Do I have free variables here? Yes, so there's going to be a matrix F next to it. And I hope, well, hopefully it's going to be on my next slide, but the matrix is going to be basically the identity and the matrix F. Okay? And so because the rows are independent, you can see from here, every row has a pivot. All right? Every row has a pivot in this particular problem. So let me, I'm going to do an example, then I'm going to show you this form of I and F. So let's take this system of equations, two equations with three unknowns. Can you see immediately why this is a full row rank? I mean, if you look at the two equations, right, they look different. Right? So R is equal to M in this case, but N is equal to 3. Right? So I have three unknowns, and I have two equations corresponding to two rows that they are independent. So before I give you the solution in terms of the matrix R, can you visualize the solution? You know, x plus y plus z equal to 3, what is that geometrically in 3 dimensions? It's a plane. So here is one plane, and then x plus 2y minus z equal to 4 is what? It's a plane. So if you have two planes, the intersection is the solution. What is the intersection of two planes? Is the point? What is it? A line. How many points do you have in that line? So this problem has infinite solutions. All right? And obviously it has infinite solutions because there are many solutions from the null space problem. Okay? So obviously we're going to have to go and calculate xp plus a particular solution plus xn. And actually you can geometrically see here the infinite solution. If you find a particular solution shown here with this vector from 0 to point xp, then you can add any solution xn from the null space. And so any solution on that second line that you see, all right, xp plus xn is a solution to the original system of equations. Okay, so let's do the elimination process for the system of two equations with three unknowns. So I take my three equations and the right-hand side, 3 and 4, and I do elimination. I'm going to have to get rid of that one above the pivot one, so I get something like that. So I am done. So tell me, spell for me precisely what is the particular solution to this problem looking at this matrix, just to be sure that we communicate. What's the solution to this problem? Give me the particular solution precisely. X equal to how much? 2, y equal to 1, and z equal to 0. We're going to take z to be the free variable. Done, okay? So you read these numbers. You don't have to do any algebra. Now, we have the null space. We have, you know, one free variable, which is the z variable. Give me one special solution corresponding to the free variable z, directly reading it from this picture. So the solution would be x, y, and z. And obviously, we're going to set z equal to how much? We only have one free variable, so z will be equal to 1. All right? Can you tell me then, reading numbers directly from this table, can you tell me what should I put for x and y? What should I put for x and y? Read me the numbers to make me happy on a Monday. So the whole vector is going to be this, this, and then 1. So what is the first two elements? Remember, you have to look at the F matrix, okay? And the F matrix in this case, what is the matrix? You can see here, you see the identity matrix. So what's the F matrix in this case? Can you tell me what is the F matrix? It's a vector, really. What components? 3 and minus 2. So in the special solution, what should I put? Say it again? No, you missed something. What do we need to do to F? Negative F. So the solution will be -3 plus 2 and 1. And there is the answer. I hope is the answer somewhere. Okay? So the particular solution you told me is 2, 1, 0. All right, that's what we have. And the special solution is -3, 2, and 1. And obviously you're going to say, don't believe you that this is actually the solution. Well, just do the algebra. You know, take that matrix A that we started, multiply it -3 to 1, and you will see by a miracle of nature it comes to 0. Okay? Because linear algebra, it's clean, right? It's the cleanest way. You will not find anything better in mathematics. Everything is transparent. Everything works beautifully because it's linear. Okay? And so nothing can go wrong. Okay. So the general solution, of course, we said we will have infinite solutions, could be the particular solution 2, 1, 0, plus any constant, I call it here x3, because that's my free variable, times -3, 2, and 1. All right, so for this case of full row rank, we always have solutions, and we saw that in this case we have, the particular example had infinite solutions. Okay, let's do another example until you get so bored with me that you decide to listen to the videos is better, or not listening to them is even better. So AX equal B, this is my A, all right, is 3 by 4, okay? So I trust that you'll be able to do elimination. How many pivot variables do we get in this problem? So actually, let me see, do I do anything further? Yes, all right. So first, you know, you can immediately see that this problem, the only way it will have a solution is when B3 is equal to B2 plus B1, okay? Because on the left-hand side, I see a row that's completely 0, and you can appreciate why the last row is 0, because if you take row 1 and you sum them up with row 2, you get row 3. So B3 has to be equal to B2 plus B1. So let's assume that that's the case, all right? So here's my R matrix, all right? So if you do full elimination, here is for this particular problem. So can you spell for me actually all the solutions so I can move on with my life here? Can you give me the particular solution immediately? -2, 3/2, and 0, all right? Give me the null space solution immediately. So how many free variables? x2 and x4, all right? So let's put x2 equal to 1, x4 equal to 0. Give me x1 and x3. x1 and x3. You remember the F matrix minus F, corresponding to the what variable? To the x2 variable. So what should I put? -2, okay? And there was a 0 there, it's okay. So -2, wait a second. You told me, okay, -2 and then what? Continue. What the second element is going to be? 1, 0, 0. Okay, and how about the x4th variable? All right, we have 1 on x4, 0 on x2. How much will be the first element? How much will be the first element? Will be +2. And how much will be the third element? -2. That's it. All right, so that's the solution to this problem. And I think, I'm not sure if this is identical to your homework problem or it is the same matrix or something that is more or less close to what you have to do in problem 7. Okay, so let me finish. Rather than doing infinite examples, I'm going to take the most general case, all right, and summarize all possibilities here. There's nothing you can go wrong. Actually, if you study the next slide, contains everything from the last 3 lectures, okay? So remember that when you do this reduction by taking linear combinations of rows, effectively this row, reduced row echelon form has an identity matrix that has to match in dimensions with the free variables, I'm sorry, with the pivot variables, okay? So the dimensionality of this, can somebody tell me what's the dimensionality of this matrix in the very general case of the identity matrix? On lecture 7, I put them explicitly so you can see them, but how big is that matrix I? Remember, it multiplies the pivot variables, and this 0 also identified the rank, right? Because we eliminated the rows that there were multiples or combinations of previous rows. So what's the dimension of I? Matrix has two, m times n. So what is for I? It's r times, thanks. And what's the dimension of f? Will be r times. It has to multiply the free variables. How many we have? N minus r. All right? N minus r. You remember when you have these block matrices, they have to match with vector x, right? And the vector x, it contains the pivot variables, and we have r of those, and the free variables that they are n minus r. So anyways, this is the most general form that you will get, all right? So in some cases, that f will not be there at all, which means the 0 will not be there at all. In some cases, the 0 zeros will not be there at all. But all possible combinations, there are 4 you can get. But this is the general form. So let me go back. So I want you to look on this equation, or not equation. There are 4 cases, 4 different types of R that you see on the bottom. So look at this. Will you agree with me that is R, if R is equal to M equal to N, then you only get the identity matrix? Right? So this matrix has full row rank and full column rank. This is very important. So the columns are independent, the rows are independent, and when you do elimination, this matrix becomes basically identity. So this problem has how many solutions? 1. So this matrix is invertible, x equal a minus 1b. The matrix is invertible. Okay, let's take now this equation of a full, so an R that looks like this, and this is, how should we call this? A full what? The second matrix, how should we call it? A full, what type of full rank we have here? It says R equal to M. Full, say it again. Full row rank, okay? R equal to M, all right? So R equal to M, in general, this will be less than N. So if it is less than N, we're going to have free variables. Okay? So how many solutions you expect in general to get from this case? If you're going to have, in general, free variables? I mean, if you have no free variables, right, you will get the unique solution the way we did there. If you have free variables, you will get infinite solutions. How about this case? All right, R equal to N. How should we call this matrix? Remember, M times N. So this is full what rank? R is equal to N means how many independent columns I have? No, how many independent columns we have? You said none? They're all independent, so it's a full column rank. I can tell you lots of students, they have never had to deal with this concept of what full row rank means and full column rank means. To them, oh, is the matrix invertible, yes or no? But here's much more than that. We can have independent rows, or we can have independent columns, or we can have both, or we can have none. And if we have none, this is the general case, right? So in this case, the matrix is not a full rank matrix of any type. So, and obviously in all of these cases, if you understand how to compute a particular solution and, you know, and how to compute the solution to the null space problem, you can answer easily all of this. So I want you to always think, do I have zeros there? If I have zeros there, to have a solution, the right-hand side also needs to have zeros. If not, no solution. If you have zeros, then you have to say, do I have an F there? If the answer is yes, how many solutions? Infinite. That's it. The rest, you know, basically it's, and just remember when you say full column rank means all columns are independent. You know, full row rank, all rows are independent. And, you know, you can connect these 4 different types of R with those definitions. Now, believe it or not, I was planning to do another 30 pages with defining the dimension of these null spaces, but I can give you a brief summary of the part of the lecture on, from Wednesday. When we say, oh, this matrix, you know, is going to be full column rank, how many independent columns? R, right? So the null space in that can exist. Can somebody tell me, so we can complete the lecture, so the null space, we had n minus r free variables, right? And we said, you remember, each of them equal to 1 and the rest equal to 0, okay? So how many independent vectors do you think I need to describe everything in the null space in general? I mean, the way we started working with the free variables by setting each of them to 1 and the rest to 0, 1 and zeros, how many, and we have n minus r of them, how many independent vectors do we define that way? N minus r. So we call n minus r the dimension of the null space. This is how many independent vectors we need to generate everything in the null space. Okay? Now, in general, all right, so I have a matrix M by N, okay? It has N columns. How many of these columns are independent? So, you know, we start with a matrix M by N. How many of the N columns are independent using the notation up to now to the class? How many columns are independent in general? How do we call that number? How do we call that number? It's the rank of the matrix. So we have R. So R is what? Is the dimension of what space? Of the column space. And similarly, what do you think is the dimension of the row space? If you look at the rows as vectors, all right, how many vectors in the general, if we start with an M by N matrix, how many independent rows can we have? Or how many we have in general for any matrix? R, all right? So we have discussed the column space, the row space, the null space, and one space that has not been introduced yet, and is fundamental, is the left null space. And obviously you can imagine that is the null space of A transpose, and then we're done. And then we will see the miracle of matching the dimensions of these different spaces, because it will tell you how any vector in Rm or in Rn can be generated by taking, let's say, you know, some vectors from the null space, you know, some vectors from the row space, and putting them together the way we have done to get these systems of equations solvable. All right, so read the rest of the slides, and I'm going to come back to these topics on Wednesday. I think that the TAs have office hours today. I have office hours tomorrow. And if you don't know how to submit the homework via Sakai, because I don't know, ask the TAs. And if you cannot find an answer, just email your PDF to me, and I will take care of the rest from there. So I'll see you Wednesday.
The homework diagram is due tonight or tomorrow night.
What does it say in the...